All right, hello everybody. As Scott said, I work at Earthscope Consortium, which operates the NSF National Geophysical Facility. I want to talk today a little bit about, first of all, who we are and what we do for those of you who are unfamiliar with us, and then talk a little bit about how we could kind of use the Juno ice field to our advantage for a testing platform for polar instruments and systems that are intended for high melt or temperate glacial environments. So first off, I'll start with a little intro of Earthscope. Let's see if this will go. There we go. Um, so Earthscope came to be in 2023 after a merger between two organizations that predated Earthscope, those two organizations being IRIS and UNAVCO. Perhaps several of you are familiar with those organizations. So IRIS was the Incorporated Research Institution of Seismology, focusing mainly on seismic support for PI experiments around the world. And then UNAVCO focusing mainly on geodetic support for PI experiments, as well as long-term geodetic network operations, largely up and down the west coast of the US, but also globally. So they merged in 2023 to form Earthscope Consortium. And in 2025, just in September 2025, Earthscope was awarded a subaward from the National Science Foundation to operate the NSF's National Geophysical Facility. So that is that we are well on our way to operating this new NGF. Some changes are still occurring, but our baseline support for seismic and geodetic support for science globally is still maintained. So what we do, this was written by one of our outreach communicators in our engagement directorate, but just to sum it up in one sentence is we give scientists tools to examine the Earth with extreme precision and better understand natural hazards and our changing planet. And that involves a wide array of support. So this is a graphic that shows all of our integrated geophysical support with instruments installed in polar environments. Our support is actually expanding to seafloor geodesy and seismology, so some instruments in the ocean. We lend out instruments to PIs who study in urban environments, water resources, volcanism, mineral resources, and so on and so forth. And with that, so the data that are collected from these instruments are all archived and publicly available. So that's a very large part about what Earthscope does, is making sure that the public has access to the data that are collected from our instruments that are installed for various projects. So a little bit more information about our seismology support. I already mentioned that our support involves data archiving. So our data directorate works on a lot of different data products to be able to archive and visualize seismic data. We maintain, as a National Geophysical Facility, we maintain part of the Global Seismographic Network. You can see the map on the bottom left here of all of the GSN stations worldwide. So with the USGS and other collaborations, we maintain that network. And then we also have a portable instrumentation services group where we lend out instruments to short-term projects, short-term PI-driven projects worldwide. And those instruments include seismometers. We also do some active source seismic support. We have magnetotelluric instrumentation and ground penetrating radar. And the geodesy support. So similarly, we archive GNSS data and borehole and strain meter data, and also synthetic aperture radar. And kind of the analog to the global seismographic network is the Network of the Americas. And also, the global GNSS network, which is the GGN. So we maintain a permanent network of instruments, geodetic instruments, around the world and largely concentrated up and down the west coast of the United States, as I mentioned previously. Um, and we also have a portable instrumentation suite for our geodetic support, and that involves GNSS instrumentation, terrestrial laser scanning, UAVs, and structure from motion. I thought I'd throw in here, this is a photo of one of our NODA stations, so Network of the America stations, installed by Mendenhall Glacier, just on the edge of the Juneau ice field, and a little data snippet on the right showing the position time series of that station over time, which is also all, of course, publicly available on our website. And then kind of the third part of what we do, which is a large part of what we do as an organization, is education and workforce development. So we provide education support in the form of materials and modules and activities and data tools for classrooms in like middle school, high school, and post-secondary education. And we also work on student and early career skill building. So EarthScope, in collaboration with other universities and institutions, develops technical short courses and workshops to develop geophysical skills in early career and student populations for people looking to go into geophysics. And then the third thing is internships. So we have different types of internships, I think actually on the next slide. Internship programs for people in different phases of their education or with different career goals. So we help to develop and support these different internship programs. Some of them are very classical internships where somebody will actually work directly with an EarthScope staff member on a project for usually over the course of a handful of months over the summer. And then some of them are more short-term field-oriented field camp internships, which is like a highly concentrated time of hands-on research experience over the course of a couple weeks. And we have a bunch of information about this, of course, on our website. So I am based in New Mexico at the EarthScope Primary Instrument Center. This is where we have a large warehouse full of the instrumentation that we lend out for portable PI experiments, and that we also send out to our engineers who are based all over the US for maintaining our permanent instrumentation networks. So we have a warehouse here. We have access to roof access for testing our GNSS antenna. You can see that in the middle photo on the top. And we do a lot of instrumentation testing just outside of our facility where we can put seismometers in the dirt and make sure that we're testing them before we send them out to PI experiments. So that's kind of a broad overview of what we do. Part of our operations is part of our funding comes from the Office of Polar Programs. So we do have a dedicated polar group that works specifically to support science in polar regions, which, as we all know, raises unique engineering problems. And so I don't know, since Iris came to be, or since Pascal came to be rather, in the early 2000s, most of our polar operations were dedicated to polar plateau regions. So environments like the picture on the left, where they remain cold, there is, steady snow accumulation, but you're not really worried about any melting. So that means everything stays frozen and stays in place. And the major engineering concern is snow accumulation. So having to raise all of the instrumentation to the surface at regular intervals. However, we have seen a reduction in instrument requests for science on the polar plateau regions and an increase in instrumentation requests for science in ablation zones or high melt glacial environments, such as the picture on the right. So this has introduced a whole new suite of engineering problems and challenges that our polar team works on. Some examples of projects that we've seen in the past handful of years. So scientists looking at capturing seismic signals of superglacial lake drainages and associated surface velocity changes using GNSS on Jakobshavn Glacier, the edge of Greenland, West Greenland. We've seen another on Flask Glacier on the Antarctic Peninsula for monitoring tremor induced by turbulent subglacial water flow. We have something happening this summer on Kennecott Glacier for monitoring glacial lake outburst floods. And then again, more basal hydrology in West Greenland on the Jakobshavn Glacier as well. So these are all unique environments with a lot of melt, a lot of water, and they also present unique challenges in terms of what their duration, the duration of the deployment of the instrumentation. So some of these are installed in the summer and removed in the summer. Some are installed in the summer, and then they have to last through the winter collecting data to then be retrieved the next summer. So you imagine if you're installing instruments on a frozen surface and then they melt and tip out, and then they're supposed to still maintain recording capabilities throughout the winter. You have to design them accordingly. So here's an example. This is on Jakobshavn Glacier, on the west coast of Greenland. So installing the instruments, the picture on the left where it looks quite cold and everything's snowy and frozen. And then on the right is the environment, what it looks like when we go to retrieve the instruments. So to kind of navigate these challenging circumstances, we backing up just a little bit, but so with the seismometers that we have, I'm not sure who's familiar with seismometers in the crowd there, but most seismometers have a very small tilt tolerance, so you want to keep them as vertical as possible in order to record useful data. And so we took this seismometer, this kind of pictured on the left. It's like looks kind of like a tin can. And one of our PIs suggested, because he had success with this in the past, that we mount it to a pole, drop it down a hole in the ice. This is again when it's still cold and snowy and frozen. And then as the meltwater trickles down the hole, it like freezes the seismometer in place and keeps it as vertical as possible as the ice melts around it. So it's kind of some shenanigans in installing these, in first mounting the instruments and then installing the instruments. A lot of kind of trying to balance how much ablation there is with how deep you install the instrument so you can still reach down the hole and make sure that it's leveled and oriented properly. So these three photos on the right are photos of installing the instruments in, I believe this was April-May timeframe in Greenland. And then this is in September. So fast forward several months through the summer, and this is what the stations look like. So you can see, the instrumentation box, the orange box, which houses the battery and the data logger, have kind of slid away, tugged on the cable a little bit. The seismometer is definitely not vertical. In some cases, it fell over in a puddle of water. In some cases, it was still, propped up on the pole, but definitely not recording useful data. Luckily, in this case, they were looking to collect data from a lake drainage event, and the sensors were still in good enough spot to do that. So that's good. But of course, we want to collect good data as long as we can for the duration of the deployment of the equipment. So that brings me to talk a little bit about like next generation technologies. So with this advent of more instrument requests for science in kind of these high melt glacial environments, we're looking into new technologies. And one of those technologies is seismometers that have a higher tilt tolerance. So here's some examples of seismometers that can handle a little bit more tilt and still record useful data. But what we want to do as a facility is make sure that but before we're acquiring large amounts of instrumentation and then sending them out to PI projects, we want to do some thorough testing and evaluation to make sure that they're actually going to do what we want them to do. So a couple of years ago, I was up on the Juneau ice field and actually tested this seismometer on the left, which is manufactured by a company called Gerelp. I tested it on the Juneau ice field. This is Echo Glacier. Of course, for those of you who have been up there, you know that there's plenty of melt that goes on and plenty of water flowing. The bottom left corner is picture is taken in front of Camp 10 on the Taku Glacier. And so I installed the seismometer next to one that we already have in our instrumentation pool over the course of, I think it was about a week or so. So really not that long. When I was up there as a faculty member. So the top photo on the right shows the instruments when we deployed them. And the point of this whole test was to have both of the seismometers tip out and we could compare them to one another. So when we came back 2 weeks later, you can see in the bottom photo, it was a very wet, rainy day, but you can see that the instrumentation is kind of tilted out and tipped out. This was a very useful test because we realized we had some sort of expectation of how this instrument would work in terms of being able to tilt plus minus 90 degrees. And those expectations were incorrect. So it actually spurred on some really useful conversations with the manufacturer. And we would like to rerun a test, obviously longer term, 1 week is not enough, in an environment such as the Juneau ice field to be able to see if this is a viable solution to a lot of the high melt problems that we're seeing and if it's worth purchasing a large suite of them for this reason. So the Juneau ice field being easily accessible and having a large, like the logistics network figured out, could be very beneficial to testing instruments like this prior to adding them to our large instrument pool. An added benefit of this is actually from this last summer when we install instruments up there. Part of the reason it's useful is to be able to test them for our instrument pool. And then it's also very beneficial to teach JERP students about instrumentation systems in glacial environments. And so last summer, we deployed some instruments and actually only for about 2 days, and we happened to capture the magnitude 7.3 Sandpoint earthquake that happened off the Aleutians. We just happened to catch it within that like less than 48-hour period. So that was really cool to look at with the students. Here's just another example of an instrumentation systems deployed in these ablation zones. So we install them as they kind of would look on the left and then come back later. And you can see in the upper right photo that the whole solar panel has tipped over, and the bottom right photo that the instrumentation box found its way into a little gully and was like tugging on the solar panel cable. So one of our engineers in our polar group is working on this new design to keep the components of the system from tugging on one another and snapping cables. He's working on a design, a work in progress, of mounting the power system and the instrumentation all to a single pole, so that the whole system moves as a unit and you're not worried about cables snapping. This is a work in progress, of course, for developing an installation method to avoid this tipping over to a high center of mass. But again, it's a concept. And we would love to be able to test systems such as these, like I said previously, prior to sending them into the field for funded PI experiments. And we think that the Juneau ice field could be a really great place for that. So in conclusion, I know it's lunchtime for y'all, so I don't want to take much more of your time, but EarthScope's Polar Group is seeing an increased number of requests from scientists to install instruments in temperate, highly dynamic, high melt glacial environments. How to instrument these sites is a big challenge. Using the Juneau ice field as a testing environment to inform bulk instrumentation purposes and system design priorities would be hugely advantageous. And of course, it also provides a unique opportunity for scope engineers to teach JERP students about geophysical instrumentation systems and data collection in glacial environments. And that's it for me. Any questions or comments?
Questions, anyone in the room or online? Esther?
Hello. This is super cool to hear about all this instrumentation capability. I was wondering when you talked about the existing and maintained databases, especially about the boreholes, how extensive is that in Alaska?
I don't know exactly how many boreholes specifically are in Alaska, but we do have network maps of all of our instrumentation. And I do also know that in the NGF, so in the National Geophysical Facility subaward, boreholes and strain meters specifically are being, the support for those instruments is being decreased in the National Geophysical Facility, while support in other areas is being increased. Um, but if you go to our website, we do have network maps of where all of our uh, permanent instrumentation sites are located. And then there are also links to how to access the data. Um, yeah. And we have a team who's working a lot on, like I mentioned this before, but developing data products for kind of data visualization and processing in the cloud. I don't know if that, does that kind of answer your question? Oh, and sorry, you
Yes.
mentioned specifically Alaska. We do, so I don't know about boreholes and strain meters specifically in Alaska, but the network of GNSS or geodetic instrumentation in Alaska is quite extensive. We actually have a facility based in Anchorage, where we have a warehouse with a bunch of equipment, and we have a bunch of engineers up there in the summer, flying out to all parts of Alaska to make sure that these stations stay online and are functioning so that the data can be made publicly available.
And can I follow up real quick? Is the database exclusively Earthscope maintained instruments, or is it also here's where, you know, like the oil companies' boreholes, for example, might be?
Yeah, that's also a good question. As far as I know, it's only Earthscope maintained. The only caveat there is for like the Global Seismographic Network, for example. Um, so Earthscope operates some of them, and the USGS operates some of the other stations. Um, so for those instances, those data, like I said, they're most likely available. I know Earthscope data is, and I can't answer confidently if other data is. But in situations like the GSN, I would imagine they are. For oil companies, so often one caveat that we have with our instrumentation is if you use it, there are some exceptions, but if you use our instrumentation, the data have to become publicly available. And we do have some private companies who reach out about the possibility of using our instruments, and that sometimes turns them away because they don't want to make their data public. Sometimes it turns them away, and sometimes they don't mind. Like we've had some companies approach us about doing geothermal explorations, and they're private companies, and they're okay with making their data publicly available. So it really just depends. Yeah.
Thank you.
There's just a follow-up question on that. What is the timeline of making that data publicly available after collection?
Yeah, good question. It's 2 years. And I think I mentioned before, there are some data exclusion policies where you don't need to archive the data. I don't know the specifics of that, but in general, it's 2 years. So scientists collect the data, you have 2 years to process it and have ownership over it. And then after 2 years, somebody from our data team reaches out and nudges you for your data.
Awesome, thank you.
Mhm. And I'll mention too, our instruments are available for NSF funded projects. They're available like right now for no cost, basically, unless you want a field engineer to come help you, then you're paying for that engineer's time. The National Science Foundation is changing their policies a little bit and trying to do more cost recovery, especially for non-NSF. So for non-NSF funded projects, full cost recovery is expected. But for NSF projects, the cost of borrowing our instrumentation is very low.
Okay, so that was great. This is Seth. And then I'm gonna do the same thing I did the last talk, just like trying to wrap it back into everyone's thought process for
Mhm.
moving forward, you know, the high melt, obviously like strikes a nerve, and it definitely hits home for the ice field, as Casey very much explained. But then the other thing, like I'm also thinking about like the high accumulation rates that we have in long-term installations on the ice field. Trying to site installations in areas that might not be, you know, plowed with 10 meters of snow. But then how do you manage the long-term viability of that instrumentation and the other hazardous environments that it's dealing with, you know, high winds, high, you know, other precipitation regimes besides snow are other things that kind of come to mind. I guess that when I think about testing on the ice field, those are things that we can certainly think about too.
Yes, absolutely, Seth. And thanks for bringing that up. So the two examples I provided are focused around high melt. And the reason being is we do have a lot of instrumentation systems or access in like in the Northern Cascades or places that have a lot of snow. So I don't think that wouldn't be a focus for us because we have a lot of engineers working on high snow load environments and instrumentation systems. However, of course, the Juneau ice field has a very, very, very heavy, wet, high accumulation snow. So I do see there being an advantage there too, also designing instrumentation systems to both accommodate melt and very, very heavy, wet snow in large amounts. So that's thank you for bringing that up. Yeah.
Great. Any other questions, comments? Thanks, Kirsten.